Hello community! Nature is intelligent to an amount that is breathtaking. But of course, humans are the real genius. I mean, imagine what other species on our planet would be sitting in a transportation vehicle that does not move at all for a minimum 2 hours every day, 1 hour on the way to work and 1 hour on the way back home. So, you see? Nature learns continuously. And now the question is, if you look here at me, can we, and I mean we as individuals and as society, learn? And you might say, hey, we need a challenge, to bring back out the best in us. We need a challenge. So, for me, the challenge today will be AI. Let me explain. If you look at this image, you might say, hey, there's a solution. We have to look at the decentralized, partially observable Markov decision process in AI to find here a solution to this. And I would agree with you because, you can imagine a city traffic network as a little microcosm of independent agent or cars, which each has its own goal and each constraints, and it is more or less pure chaos. And this is the example of a decentralized, partially observable Markov decision process. Individual vehicles acting as autonomous agents have only a limited perception, maybe just 2-3 cars in front of you, rely on sensors to gather information about their immediate surrounding, and their objective is simple to reach their destination, as simple and without any collisions at all. Now, the traditional multi-agent reinforcement learning approaches, they have a hidden assumption, and the assumption is synchronous decision making. And here we fail to capture this because our traffic flow is not at all synchronous. Our cars do not move in lockstep. Some accelerate, some brake, some change lanes independently. And what we have a dynamic and even more horrible, unpredictable environment. And exactly in this moment in time, I got a beautiful response from one of my viewers. And the viewer says, honestly, out of all the research papers published, how many of them do you think really are significant? It is hard to keep up with the pace. And I thought about this and but the solution is not easy. Let me give you an example. Have a look at this paper. 1st of September 2024. Cooperative path planning with asynchronous multi-agent reinforcement learning. And I was in the mood, so I took another paper. I selected this hybrid training for enhanced multitask generalization in multi-agent reinforcement learning. And then I thought, okay, we take 3 multi-agent framework for collective intelligent research. And I decided I want to go a new way. I want to improve how I present content. I want to bring all of these papers in one environment, in one mind frame, if you want. And classically, I would set out and say, okay, we start with the symbol, so what parameters do we have here in these papers? And we would go here with this, but let's do something different. It is about the core idea. So what we have a situation where we have a multi-source destination, shortest path problem in mathematics. This is it. This is all that we have to solve. Now, if you think about this in the easiest case, we have a lattice structure for a simulation, a computer simulation, with about only 100 nodes. But of course, real time, it is much nicer. Maybe you have here, imagine this is here a map of some little villages somewhere in the countryside, and you have here a village and another color decoded. And then you have those community are connected by certain roads, and this red indicator here tells you that this is the only in and out here to this particular community. This is the road network. And here we expect that we have a bottleneck if there's a heavy traffic, because if somebody wants to go from this district to this district in a city, well, this seems to be here the fastest connection, no? So now you understand exactly what we are going to focus on today. Multi-source destinations in parallel cars moving. So what we have AI agents that incorporate in real time while dealing with changing environments and new traffic conditions every second. Every second the car in front of you is either accelerating, braking, or whatever. So we have to have a mathematical description that is a little bit more dynamic than we used to. So we have now a complex routing problem with multiple vehicles, we call those agents, and they travel from their sources to their destination through a shared road network. And the main challenge here in, if you notice, in prediction, not the weather, but the traffic is, hey, where does the network, the road network, reach its maximum capacity? Where we will have simply a no-go traffic. So too many vehicles on one road segment will lead to congestion, slowing everyone down. And you know what? Because we want to make it a little bit more fascinating, you say, hey, my goodness, I have a brain. I want to use it. I want to crack up here my intelligence from 4 of 10 to 6 out of 10. So we will not use a central intelligence. And you say, yes, this is it. Because we will move over in AI now to a swarm intelligence. So all these little minions, we add intelligence to our little minions. And we do not need here the evil Gru as a central intelligence. How we do this? Now you know the traditional multi-agent reinforcement learning that I have a whole YouTube playlist on this. Don't watch it. But just to know, they have a hidden assumption of some synchronous decision making, and this does not fit well at all in our dynamic environment like a chaotic traffic network. Plus, we have no real-time decision. We have a central intelligence that looks back at 365 days of traffic and says, okay, I have here a mathematical apparatus, and I say there's a probability that on April the 12th at 6:50, whatever in the morning, we will have a similar situation. But this is not the case if we have local sensors. Plus, if we have a complexity of a city of 1 million inhabitants, the computer simulation breaks down because the compute complexity does not scale at all. So, NVIDIA has no GPUs left anymore, and we cannot afford them, so therefore we have to come up with a clever solution. No, you have to come up with a clever solution to this problem, and I'm just helping you to find it. So again, here we go. So the main challenge here is that the network has traffic capacity constraints. You see here, this crossways here from one community to the other, from this road network to this road network. So too many vehicles on the road, site congestion. But think about it. If we change the hidden idea and we move from a synchronous to an asynchronous process in our multi-agent reinforcement learning, this could be a way, and yes it is, to help us here with our asynchronous nature of decision making, given local sensors, local information for the global network. So let's talk about some asynchronous multi-agent reinforcement learning. And we said, yeah, finally some term that is a little bit more challenging. So here we go. We have here, imagine a city, and there's a district 1 in the city and a district 2 in the city, or this is here the center of the city. And now you have blue cars and red cars and pink cars, and you have a feeling what we're gonna do. We start at some point, then we move along the route on roads, and then, yes, you got it, we come to a destination. And then we have another car with a red car, and this goes over here and has a similar destination close by in this community, R3. And then we have a car that starts in R3 and goes here different pathways forward. So you see, and this happens all in parallel, asynchronous. And now we just have to find a mathematical network that will describe all of this and give us a prediction for the future. As simple as can be. So what we do now is no central intelligence. And you might be fascinated by this idea because, yes, it means we have local decision making. And now there's a little twist to the story, because if you think that an agent is a car, no, we make it a little bit clever. We have here this community, this sub-region, this district here, or this center of a city. This is now an agent. So we make a region an intelligent agent. So we have a local, if you want, agent, and he controls here, or he, she, it, controls here the prediction for an asynchronous chaotic system of cars. So each region can focus on its local routing task and cooperate with the neighboring region to plan inter-region routes. So you see exactly what is happening. We focus now on the local perspective, but we say, of course, this car, when it starts, it wants to start from this community, move over to this community. So how we do this? Do we start it first in the little region, in the local region, and project out, or do we do the exact opposite? Now, the first step here, if you run ahead and you say, yes, I have an idea, is of course, then in this asynchronous multi-agent reinforcement learning is to divide the entire road network into multiple regions. And those are our subgraphs. And now you're smiling because you know what's coming. So each region, our subgraph, can be treated as an agent that independently manages the routing decision for vehicles within its boundaries. And what we achieve, why we do this, because we want computational scalability. We don't have to compute a network of thousands and tens of thousands of traffic nodes. But suddenly we only have, 100. Much nicer, higher parallelization, beautiful. This is what we want, scalability. Manage the entire road network as a single entity would simply be too computationally expensive. So we have a two-stage routing plan. And after they tried the asynchronous multi-agent reinforcement learning from the bottom up, now they decided, hey, we have a better solution if we start here from an inter-region planning as step number 1. So the agent for the region where a vehicle starts, let's say here this red one in R1, decides which neighboring region the vehicle should move into next. Now the idea is simple. If there's a road network available at this particular time of the day, this is the shortest connection from R1 to R3. If not, yeah, there's some other option available. So how we do this? After we decided where's the start point and where's the end point of our ride, our agent here in the regions now start with an intra-region planning. So once the inter-region decision is made, the agent plans now the vehicle's exact path within the region towards the next boundary. So you notice in physics that if we have here an environment that we know and that we can have some influence on, we say, okay, we just go to the fringe of our environment here. We just go here to the furthest path that is still in our decision horizon, and we say, and then we hand it over to another agent, R3. So you get already maybe a little bit this idea of a hierarchical routing approach, because this simplifies yet a complex problem by breaking it down into smaller steps, deciding which region to move to next, and then planning within that region. Now you immediately understand this is not enough, because if you have just local intelligence, what the mastermind, the central intelligence did, it had an overarching effect. It could determine a global state and integrate multiple communities. And now exactly this is what we're going to do now on a decentralized intelligence. So what do we need? We need a global state of our system, and then we have a lot of local states. But how do we bring them together? And you might have a beautiful new idea. You say, listen, we operate all the time here with our vector things. So let's do the same. AI is not so complicated. We just use the same tools. Global state is a low-dimensional vector representation of the entire road network. And it encodes information about the traffic condition on all the different roads across the complete network, how congested it is, at what time of day is what happening. You understand this. And the global state helps now the agents to make decisions that account for the broader network rather than just their immediate surrounding in the environment. But of course, if we have now the complete overview, we have a real dynamic core in our cell, in our environment, R3 here. So the local state is also specific to the region where the agent here R3 is operating, and we have to have the global state providing here the overall view of a network, otherwise we can't decide to which community to move next, and all the local observation. All the little mini details. And if we have this kind of information encoded, and yes, tensor network, tensor flow structure, whatever you want, we have a decision-making process here in our asynchronous multi-agent reinforcement learning framework. And how we do this? We have an actor network. And this is a complex network. Is responsible for making now our decisions how to route each and every individual car, given that there are maybe 100 different cars in parallel at the same time on the same road network, and you have to route them too. So in general, and we stay here at a higher level, it takes the local state and the global state as input and outputs here an action. Which cutting edge, so which road to take to select for a vehicle to enter the next region. And this is done in coordination here with the complete knowledge of the other agents. And then if we have an actor network, you know it improves the performance if we have classical AI, a critique network that evaluates now the action made by the actor network. So we have another LLM, for example, and now GPT-4 Omni is criticizing Google Gemini and says, hey, wait a minute, Google, I look here at your recommendation for these 101 cars, and maybe, we can optimize this and this and this, and we have a better flow if we turn this around, and you get the idea. Critique network assigns now a specific value to each action based on how good or bad that action is from a global perspective. And the critique helps now the actors improve its decision making by giving feedback on whether an action will lead to a congestion or to a beautiful traffic flow. So you see, now it gets interesting, but careful, because we have two phases. We have the training phase of the complete AI system, and then we have the deployment phase. And the critique network is here really operational and of value in the training phase, but more about this later. We need another one. We need another tool, because otherwise it would not be interesting. We need an asynchronous trajectory collection mechanism. And you might say, why? Well, we need memory. Each time an agent takes an action, it logs simply the trajectory. This means the state, the action, and the reward. Was it fast enough? Was it really achieving here what we set out to do in its goal? And all of this data is now coming into the local buffer of our local agent. These trajectories are stored asynchronously, meaning each agent data is collected as soon as it is available, as the action has been done, without waiting here for any other agents, because they are outside of our beautiful logical cell. Now this method reduces now redundant data, and it improves here the training efficiency. Now, if we look a little bit more closer here to this actor network for cooperation, there's a little hidden complexity. And I'll try to make it as simple as possible, because we use something that you know from the history of AI. I don't know, 10 years ago, we had gated recurrent unit before we had transformers in the age of the dinosaurs of AI. And this gated recurrent unit is here processing multiple routing requests from different vehicles at the same time. And you say, why we need this? Because this GRU structure helps the actor to understand which vehicles are competing for the same road segments. If 500 vehicles start here and they want to go from V2 to V8, our actor has to know about this. So GRU helps here in a timely manner to understand here the competition that is going on, and the beauty is it is a simple system. So the actor networks assign higher probabilities to roads that are less congested, helping here distribute the traffic more evenly to avoid bottlenecks. Plus, yes, we have another tool in our toolbox. My goodness, I always forget this. There is, of course, a problem. Whenever we have real complex graph, in this graph structure, if we have an AI going crazy looking for routes, this AI can come up with loops. And we do not want to have loops. And we don't want to have infinite loops where the system says just, ciao, I'm gone forever in my little loop in the graph network. So therefore, we need to take care that the system, that the vehicles or the action is not caught here in loops. And we do this with a reachability graph, rather simple. Reachability graph prunes out invalid actions that might lead to our loops. So we only focus on valid routes and not routes that are not possible. So whenever a vehicle reaches a new region, the agent consults its reachability graph network or graph to ensure that its routing decision won't send the vehicle into a loop structure. And then if we have this, if we have the architecture and we have our tools and we are so proud of ourselves because we think this is it, now comes the important phase of the training of the model. Now we have to provide the training data. We want to have here maybe a different level of complexity. At first we start here only with one car here, just moving inside of our logical cell R1 here, and then we do it, a car moves now to a second cell, and then we do a car moves to this cell, and maybe comes back, and we start to increase the complexity little by little in our training. But the model is rather complex, so we have to focus, what do we train for? And there is a beautiful paradigm, a main idea, that it is called for years now centralized training, decentralized execution. And this is what we're going to use here in our asynchronous multi-agent reinforcement learning approach here. Because during the training, now that we train the complexity of our AI system, the critique network has access to the global state. It knows everything. Information about the entire road network, because since we have no central intelligence in the operation, in the training, we have to have the knowledge how all of this region work together. So this is now done by our critique network. This is the role of the critique network, providing accurate feedback to the actor network. Now during the execution, the second phase, the agents operate now independently, based only on the local observation. And they no longer need here the global state, because they have learned enough their policy. We hope that their policy is enough grokked, that they have a performance, let's say, in their policy optimization of 95%. And then we have this policy, and then the system is able to scale to the real-world application. Now, what we achieved with this little bit of beautiful complexity of asynchronous multi-agent reinforcement learning. We have a scalability, we have an efficiency, and in the training phase, the actor network ensures cooperation between the vehicles and the regions. So our sub-region, our agents understand that they have to handle here requests with the other region, and they learn how their internal path optimization in the logical cell is connected here with a request that a car maybe will just pass through the region or find a location within its logical cell. Scalability, efficiency, and cooperation, beautiful. Now for my green grasshoppers, I know this old stuff, gated recurrent unit, is a type here of a recurrent neural network we used in the olden days to handle sequential data. We did this before we knew anything about self-attention. The easiest idea was gates. A gate, door, you can enter here information, and a gate controls simply the flow of the information. That's it. And we had 2 gates. We had later 4 gates, but never mind. We had a reset gate to decide how much of the previous information to forget. Because if you only put information in, suddenly the storage is not enough. It can't hold the information. So we had to open a gate to let unimportant information out. And then, of course, we had an input or update gate and decides how much of the current information, if we have a huge data stream coming in, what elements of this data stream, what elements of this current information to pass forward. So, old idea, real nice, we know how it works, great. If you want to know in the history books of AI, they are similar to LSTMs, the long short-term memory units. But the benefit is those groups are simpler, computational simpler, easier to code, and they perform often better in practice if the complexity level is not too high, and we don't have a high level because we have multi-agent that distribute here the complexity. Each request contains information about the current location of a vehicle, the destination of a vehicle, the current traffic condition on the roads that a vehicle may take. So you might ask how we do this in AI. Well, surprise, surprise, we have a feature vector, which we call also an embedding in a vector space. And you might say, amazing, who had this brilliant idea? Yes, it's always the same, using a neural network, multi-layer perceptron, and this embedding serves as the input into the GRU. And after multiple requests, yes, you get the ideas, and the hidden state acts as a memory, and you say, what a surprise to us. Now, I want to give you more information about the actor network overview. We have 3 components: the road network encoder, the plan request encoder, and an output model. And those work together to produce a probability distribution over all available road segments, exactly what we are looking for. So let's have a look at here, the first element, road network encoder. It is simple to task encoding the road network so that the actor can understand the traffic state of the network and make decision. So what we encode, we have here the road network is composed of our cutting edges, and for each cutting edge, we have now a feature vector that describes the current traffic condition on this particular edge. This means the speed, the congestion, the capacity, every data that we have on this particular piece of road. How is it encoded? You're not going to believe it. Here, this feature vector is passed through a multi-layer perceptron, which then transforms here the feature vector into a latent embedding. Again, we have it. And this embedding is here a beautiful, compact vector representation of the road segment feature. And we can work with vectors. Combining now all those embeddings, so for all the cutting edges in a specific region, their embeddings are concatenated into a single road network state embedding, which represents here the traffic state of the entire sub-region. Beautiful. Second element, the plan request encoder. Each vehicle sends a plan request. It says simply, hey, I want to go from point A to point B, and the actor, of course, needs to encode this request to understand the destination and the path that the vehicles are aiming for. So again, we do a vector something. So for each plan request, the requested vector, which simply describes the destination and the current state of the vehicle, is passed through another MLP to get here the request embedding. And then simple multiple vehicles might be heading towards a similar or maybe an overlapping destination. So therefore we need the model cooperation among the requests to avoid sending all vehicles down the same road, the same path. And exactly to handle this, we use here our gated recurrent unit, as I already have shown you, that summarizes here all requests for the region at that particular time step. Now the output model is simple. We combine all the embeddings and produce an output. So what we have the road network embedding, we have the embedding for each individual plan request, and we have the embedding summarizing here all the requests. So the actor more or less needs to combine those embeddings to decide which cutting edge, this means which road segment each particular vehicle should take now. So at first we have to score here each cutting edge. You got it. We have an MLP that generates here a score vector where each element represents a score for a specific cutting edge. For example, a high score means that the cutting edge is a good choice for the vehicle to take. And then we apply a softmax, what a coincidence, to create a beautiful probability distribution. So the scores are passed through a softmax function which converts them into a probability distribution. And this ensures that here this element selects the cutting edge with the highest probability to minimize the travel time and avoid suggestion. If only if some few vehicles are heading toward a similar destination, the actor, of course, assigns a high probability to the shortest available path. However, if you have many vehicles that are heading down the same area, the actor assigns now a more even probability across multiple paths to avoid suggestion. We have reached our goal, and here you have now the visualization of this complete process. If you want to see this in a little bit more detail, this is here from the original papers. This hidden state is used by the actor network to generate now a probability distribution over all possible actions, which means which road segments or cutting edges between the communities should this particular single car now take. Yes, GRU helps the actor network. Yeah, this is the most important. GRU helps the actor network understand how different vehicles might compete for the same road space. And this allows here the actor to balance here the load and avoid congestion on popular routes, given we have a dense enough network of roads. So if one road is reached maximum capacity, there are other alternatives, and this is not, hopefully not, the only single road connecting here two communities. Now, the whole visualization of the process, here you have it. Whatever I told you in this video, here we start vehicle, inter-region routing, planning, intra-region routing, actor-critic, critique different actor structures. Here you have it in a simple visualization. But what I would like to stress is here that the main idea how we do here our decision. So we do have a centralized training and a decentralized execution paradigm. Let's look at this again, because that is important. Now we start with our centralized training. So during now the training phase, that we have tons of training data, all agents, you remember this correspond to our sub-region in the road network, share a centralized critique function. And I told you, this has access to the global state because this is what our central intelligence was before we moved here to the swarm intelligence. So in the training phase, we have to have the complete information of the complete network. And this is our critique. Sees the entire road network, our traffic conditions, provides feedback on the joint action of all agents in the subregions, allowing it to evaluate the global outcome of all decisions. And this feedback now is essential for ensuring that the agents now, our sub-regions, learn to cooperate with each other, minimize congestion, optimize the road. You know this. Now the second part is our decentralized execution, the operational. And here, those sub-regions act independently using its own actor network. And this is the beauty. We do not have a central intelligence anymore. This means that each sub-region makes routing decisions based only on local observation and the global state it received during the training process. So finally, we got rid of a central planning authority. Finally, there's no central authority, no master agent anywhere coordinating now the action, because all our agents now are intelligent enough and have learned enough to route here to an optimization. Each agent in the execution is now autonomous, making decisions based on its own local state, the current traffic conditions, the current incoming requests from the vehicles, the current operational requests from all the vehicles in its logical cell, and some limited information when and how neighboring region will send in new cars on particular roads. So, if you want to, for my green grasshoppers, very easy. What is this? Centralized training, decentralized execution simply says each subregion, each agent here in our multi-agent network has its own actor network for decision making during execution. Reduce here the overall system complexity and we get a operational computational complexity. And the critique is centralized during the training. We need this. But decentralized structure is not present during the real-time execution. Let me stress this again. What is happening in the learning and this memory component? Because you know a typical reinforcement learning loop here for my green grasshoppers: action, reward, memory, update, critique, feedback, policy improvements. In the asynchronous learning, nobody learns at the same time. Everything is happening in independent timescales. This makes it a little bit more challenging because agents need to learn, as we said in the beginning, as you said in the beginning, from partial real-time experiences rather than waiting here for a synchronization step from a master agent, from a central intelligence. So this asynchronous trajectory collection mechanism that I told you ensures now that each agent updates its policy based on the local rewards and state it encounters, even if other agents are operating at different times. And that is fine, because maybe at 7 o'clock in the morning in one district or one part in your city is still sleeping while the other part of the city is still bustling around. And this allows the agent to learn continuously in real time as new vehicles enter the region and make routing requests. So, if you want the summary here for my green grasshoppers, this is what we learned. There is something where I have a feeling we can become a little bit better. We can improve this system. Because think about it. This training phase. The agent learns from the local rewards and the critique. And during the training, everything is fine. No? Each agent learns from its local rewards. Beautiful. And each agent receives feedback from the centralized critique. Everything is great. But then, after the training, remember, the local agent now applies their learned global policy, whatever they learned during the training. But now, if you think about it, you would assume that in the training data, it was the complete set of possibilities that can happen. And maybe you will have a flooding on road number 17. And maybe this was not in the training data. And then maybe you encounter problems that were also not in the training data. So I think the next step to optimize this system further is maybe after some time again do a training phase where everything that happened, the main events that were not in the original training data, now in the second training run, we put in all our things that maybe we forgot in the first run or that we encountered here in real time. And maybe in winter time, there was some problem here with the snow, and you get the idea. So I think if we say, hey, training happened and then this is it. For our policy level, I think no. I think maybe there are certain times where we have to open up the training phase again to optimize the training to new things. So if you want to have a more detailed look after I've given you just a feeling of the content, this is here, the paper that we just talked about. But I showed you the second paper already and you said, yes, my goodness, so now we are warmed up and now we are ready for the real interesting stuff. But hold on, because I have another idea. I want to continue with my story with this city and the traffic in the city. And I want now to increase the level of complexity a little tiny bit and you will enjoy it. Imagine, this is here a block. And let's go crazy and say 1, 2, 3, 4, 5, and 6. These blocks here, they ordered something from somewhere and we have to deliver the goods to, I don't know, let's say 100 people living in those 6 blocks of whatever this is. So we have a transportation topic and we have a delivery logistic topic. Now we have AI, so we are somewhere, our logistics center is somewhere outside of the city. So we have a truck that goes from our central hub, loads up all these 100 items and drives now in the center to the heart of the city. And let's say we have here a car that we just looked at, an urban traffic system. And let's have the idea that here inside of the truck here we have 100 drones. And these drones have their parcel attached to them. And then if, this is now an optimization problem, if the truck reaches now a certain critical position, let's say here, the truck opens up the top and 100 drones fly out. And now these drones can fly for 5 minutes. They have an energy limitation because our next step will be to optimize the time and the energy that we use and the pollution, and you get the idea. And now 100 drones located here have to deliver 100 parcels to 100 addresses here. So you see we have a combined topic here of a road network and then of a drone network. And now the question is simple. What can we learn from one system if we already have here the system of the road? Now you might think here in this local environment, you might think, you know what? I want to do the same. I want to have a local intelligence only. I want to have my 100 drones. I give them a little bit more of a brain, but they do not have a central controlling unit. I want that this swarm learns from each other and they behave now differently. So let's do this. So our goal is to have our 100 drones operational at a specific location. Great. Now, if you think about this in an abstract level, we have here our road network. our level with the urban transport by cars, by trucks, by buses, whatever. And then we have now suddenly another level in our transportation system. And this is done by drones in the simplest idea. And as I told you, yes, we will look here in the next video in the cross-modal AI system interchange. But yeah, we are only a civil channel, so I'm not going to talk in this channel about any military multi-drone operation. We talk about here the urban, the civilian, where we have no central intelligence, neither in this level nor on this hyperplane. Great. And now we take here this paper. And I've chosen this paper. Normally I would not choose this paper because it's just by one author. But the idea in this paper was nice. It was a simple but beautiful idea, and I have to show you this. And this is the reason why I constructed now this new scenario in the city. So we're talking here, Freie Universität Amsterdam, multi-agent framework for collective intelligent research. This is our drone example. And now we build the intelligence differently. We build it simpler. We want to have that our 100 drones have an emergent intelligence. How we do this? Now, we look at our biology class and we say, okay, the ants, they have this swarm intelligence, or if you're some birds, if you're in Rome at a beautiful end of August in the evening, you see amazing things in the sky. And you say, can we do this with our quadcopters? And quadcopters now, if you have 100 or 500 of them, in the night, I was in Singapore, they have beautiful light installation in the sky with hundreds of drones. But they all have a central intelligence. But now we want to have a system where the drones communicate and learn from each other. I don't want to have a program before any drone starts that predefines exactly what to do, because in a local environment you might encounter problems, roadblocks, situations that are not in your original training data. And what then? Then the drone stops working and comes back? No. The drone has to use its own local intelligence to find a local solution. And this is exactly what we're going to look at. So our story begins here with drones, small agile machines. I get, you know what it is. And they have a collective action set. And yes, you got it, we have an action space that we build out in mathematics. Multi-agent framework developed now for a drone coordination system. Drones operate under decentralized architecture. Each drone makes decisions based on the local sensor perception of the environment, following, and now the beauty, even simpler rules like avoid a collision and move to the point of interest. But then we see when these drones now start to work together to communicate, something extraordinary will happen and they will begin to self-organize on the lowest possible level. Are you still with me? Because now comes a little bit of mathematics. We do this by field modulation theory. This is now at the heart of our simplest emergent intelligence. So what do we do? Imagine you have a field and you apply positive or negative fields to present here nearby agent or obstacles. Drone can make local decisions that contribute to a global coordination if one drone knows exactly where the other drones are. I will show you here an example in a second. Field modulation theory, I will show you this, has one form, and this is gradient ascent or gradient descent. We choose here ascent to ensure that the drones move in the direction of valuable information or higher rewards that we now encode in a three-dimensional field structure, and thereby avoiding the negative areas or obstacles or other drones. And this will bring us a form of a self-organization, the lowest level. The drone exhibit behavior that seems far more intelligent than what their individual capability suggests. And this also shows us that this system shows that the emergent intelligence doesn't need a central control. It arises naturally from a local interaction of multiple drones and multiple, let's say, points in the environment. So I think we have to explain field modulation theory and the gradient ascent here. So this is Simple. You know this from backpropagation of large language model. My goodness, yes, we have this already in AI. You know gradient descent of backpropagation, and this is it. My goodness, explained. So think of it as the drone's way of sensing its environment. It's applying here a Gaussian distribution, a mathematical distribution, to its perception of maybe nearby agent or obstacles. Maybe there is a building in the way. And we have here, you see a negative one, but we also have positive. So positive fields mark a reward, higher reward, like points of interest where the drone should go to or fly by. While negative field signals like this here, they signal here a danger zone, places to avoid. So each drone now makes a decision. And you might ask, but how this little tiny brain on a drone, how can it make a decision based on a large language model if it has to do an autonomous local decision? Now it can't, simple at the moment. So we have to design now a system that is so simple, like a gradient ascent, that the drone simply says, hey, I follow the highest gradient ascent. This is it. So the drone moves now in its decision making where to go to, where to fly to. They move toward high value areas, avoiding collision by reacting to the negative fields of nearby agent. And you know what? This is such a simple and elegant solution to a complex coordination problem. I want to show you this here by the original publication. So you have here a positive field modulation. You see this here if you divide it, for example, on a grid for a drone. Very simple mathematical operation. And you see exactly here in the middle you have, if, I don't know if you can read it here, you have the reward. And this has the highest value of reward is yellow. So the drone knows exactly where to go to. Now we can do this here with the negative field modulation. And of course, if you have multiple fields and they interact, you know exactly where the drone should go to. The drone decides to go to the gradient ascent and fly in this direction and not in this direction. Now, I asked here ChatGPT, I said, hey, help me to explain this to green grasshoppers, Gaussian distribution in this perception. And this is the formula, and this is what ChatGPT tells you. Beautiful. And then I ask here, how can I put this in a kind of a code? And here GPT-4 was so nice and gives me here the class of the agent with the definition here, or with the function of perceive and act. Then we have here, we apply the field modulation. We generate here the field map that you just have seen at 3 dimension for the agent using the positive or the negative Gaussian field that I just showed you. And then we just have here another function that defines here how to decide what action to take. So the drone here in this code chooses here an action based on the highest gradient in the field map, and it follows the gradient. It can be that simple. So you see the architecture, and this is why I wanted to show you this study. I like this because it is a simple but beautiful but powerful idea without any high computational complexity demand on the drones. So what we have, what are the key components of our system? We have a controller. The controller is, if you want, the brain. Algorithms embedded in the agents that decide which actions to take. And as I showed you, this hill climbing controller or gradient ascent follows the gradient to perceived rewards to make the decision about the movement. Simple. Of course, we have to have a communicator. So this handles the decentralized information exchange between our agents, because the agents have to know where the other agents are and what are point of obstacles and so on. So this includes broadcasting now their local position at each time step and receiving information from neighboring agents or other points of interest that have been detected in the local neighborhood. And of course, we have to have a log handler. This is responsible for recording the data, such as the agent position and their action at specific time and specific places. So they can also visualize here the real-time trajectories of our flying agents. Now, I always think this in simple terms, so I just imagine that on this drone attached is a little phone. This is my communicator. And you know, this from the weight and from the complexity, hey, a phone is just perfect. So Officially, it means that each agent has its own communicator, which manages now the sending and the receiving of the messages. And the communicator allows the agent to exchange information about their position in the environment, information about certain points of interest that the environment dictates, a building, let's say, and their local perception, so their perceived field modulations based on what they sense from other nearby agents and their sensors and the environment. So you see, this communication network is, this local communication network, this low energy communication network is now important, and it is embedded within each agent and handles here a message passing in our graph network. So you understand immediately. So the controllers are now our local decision makers based on the idea how to make decision. Controller make decision in real time, process information such as the drone position, the velocity, the position of nearby agents in the environment. Depending on the controller used, the drone might follow here a predefined trajectory, in this case, adjust its trajectory based on a reward-based optimization. Remember, we are here in multi-agent reinforcement learning as our hill climbing controller, and now this would be the next step, but unfortunately, it is not presented yet in this scientific AI research paper. And the next step would be simply to scale up the complexity of the decision-making architecture to a DQN controller for reinforcement learning. But we don't have it yet. So, this process resembles reinforcement learning because the agent is effectively seeking to maximize the cumulative rewards by following the reward gradient. This differs a little bit from the typical RL implementation, and no neural networks are used. This is the beauty. This is the elegance of this simple solution. The drone does not rely on a deep learning model to approximate here a value function or a policy. It just uses here the gradient-based decision from a predefined map that is continuously updated by the communicator protocol data. And we have a simple rule-based approach. There's nothing complex to learn about the decision making. We have simple rules. Isn't this beautiful? And yes, of course, the next step to upgrade our system would be neural network, deep Q learning, policy gradient methodology that we know how to handle. But for this little drone, this little energy reduced drone, we have to be careful that the complexity of the computation does not become too much energy dependent. So, very simple. So why use a simple controller-based reinforcement learning instead of here a neural network? It is simple, it is efficient, it has a low complexity of the task, and it is absolutely working. Yes, of course, theoretically, you could integrate here a deep Q network or any other neural network-based thing. Yes, of course. But the actual system works. And for my green grasshoppers, this Q sigma, this Q values here, the DQN approximate here the Q values, expected cumulative future rewards for each action in a given state. So instead of choosing here the action with the highest immediate reward, the drone would then, in this update, the drone choose the action with the highest estimated long-term reward. Plus, our DQN introduces here the concept of an experience replay. So this means that over time the drones could learn more efficient strategy for navigating more complex environments rather than being stuck with a pre-programmed decision-making process. So the future is clear. The path to the future to optimize here the swarm intelligence for drone is clear. So there you have it. Now, suddenly, in this one video, we have the level of the urban transport by cars and trucks. And then we talked here about the level of urban transport by delivery of parcels by drones. And remember, in both cases, what is the beauty? We had no central intelligence. This was done here by a complete decentralized network by swarm intelligence. And you saw that in this drone swarm, let's call it, we saw how local observation guide decentralized decision-making for each and every drone of the group. But what if we want agents to learn across multiple tasks and generalize to really unseen environments? We increase the complexity, and now we have to provide more knowledge to this little drone. And there comes in now the third paper, but I think this video is already long enough. Just allow me to tell you that the next paper will be presented in the next video. And we will enter now a hybrid multi-agent reinforcement learning, building on these two papers that we just read, that we just understood together. And now we build on top of this, and we build a hybrid network, the next step, because the innovation now will lie here in the combination of offline skills with online reinforcement learning to build better, more adaptive, more generalizable agents. Now, isn't this beautiful? So, the future of AI is not just about perfecting here some individual single solo systems. I think it is about building networks of intelligent agents, like the road transportation mode or the drone transportation mode, or maybe we will have a look at energy transportation in urban environments, or water transportation in urban environments, or pedestrian transportation modes. All those networks of intelligent agents that can coordinate, share, and optimize themselves collectively. And I think for me, this is the beauty of AI. And I want to build a kind of an urban AI ecosystem that hopefully will redefine our cities, making them more efficient, more sustainable, and more responsive to human needs. And the option is, to a 90%, we will fail. We will fail as a society, and we will fail as humans. But there is hope, because nature is intelligent. And this was the first sentence of this video. And if you remember here, this is me and this is AI. And the more I know about AI, the more I know that gravity is here for a reason. And I mean this on a personal, individual case. Or we can achieve to build a unified AI ecosystem for our future.